All right, so this is the third video in chapter 7, where we're going to talk about the second confidence interval technique, where our data comes from is normally distributed, but I don't know the standard deviation or variance, nor do I know the mean, and I'm trying to come up with a confidence interval for the mean. So you pause, copy this first panel down, and then press play. All right, so population's normally distributed. We don't know the mean, but we'd like a confidence interval for it. And we also don't know the variance or the standard deviation. So in the previous video, we talked about William Gossett, who came up with this t-distribution. And we're going to call it a t-distribution with n-1 degrees of freedom, right? And that's going to really nicely fit sample mean minus population mean all over S over root n, okay, where S is the standard error of the sample, okay? Now, we use n-1 degrees of freedom, and where that comes from is we're going to be given n data points, and we have a fixed population mean mu, which we don't happen to know, but it's fixed. So the idea is that if you know n-1 of the data points, that uniquely determines the final data point, like if you're God and also had mu. So that means if n data points, and if you happen to know mu, then all I need to do is tell you n-1 of the data points, and you can calculate that final data point, assuming the data had mean mu. Okay, so that's where the n-1 comes from. Okay, now here's the result. And it's going to look very similar to the result we did when we knew sigma. All right, so we've got this random sample from the normal distribution. We don't know sigma. We're looking for a confidence interval for the population mean, and it's going to be given by x bar, sample mean, minus q times s over root n, x bar plus q times s over root n. All right. So that looks almost exactly like it did in case 1, except I had sigmas instead of s's. But there's one other difference. The q, the quantile, denotes the 1 minus alpha over 2 quantile of the t distribution, not the normal distribution, of the t distribution with n-1 degrees of freedom. And we often denote that as t sub alpha over 2. And just to recall, S is the sample standard deviation, the standard error right there, okay? So a very similar looking formula, but we're using the t distribution instead of the normal distribution, and we're using S in place of the unknown sigma, because remember, S was the unbiased estimator of sigma. All right, so let's do an example of this. So you pause, copy, unpause. So I'm going to take that random sample that we looked at before, containing 2.8, 3.2, 3.6, 4, 4.8, and 5.1. And let's assume we believe it's drawn from a normal distribution, but I don't know mu or sigma. And I'd like an 80% confidence interval for mu. Okay, so the same problem as before, but now I don't know sigma, right? Well, so I still have n equals 6. X bar is still 3.92. And I can go through and calculate f. So 1 over 6 minus 1 times first data point minus the sample mean squared, second data point minus sample mean squared, sixth data point minus sample mean squared, and I get 0.9. All right. Now I'm going to use the t distribution, so I need to know the degrees of freedom. So it's n-1, 6 minus 1 is equal to 5. And I also need that t value, that quantile value for q in the formula. So I'm looking for an 80% confidence interval. So I believe I'm looking for t.1 with 5 degrees of freedom, right? 80% means alpha is 20%, so half of that is 10%. So I'm looking for the spot where there's 10% of the area of the t-distribution above the spot and 10% of the t-distribution below minus that value, okay? All right, well, here's how I do it. I always use R. I'm looking for the quantile of the t-distribution. I'm looking for the 90% spot. So 90% of the area is to the left of the spot, leaving 10% to the right of it. And 5 is the degrees of freedom. So I got to give it the quantile and the degrees of freedom. So type that into any R shell you like, and you should get 1.475. And now I can simply use that formula you've got copied down from the previous panel. X bar minus my Q value. There's S, there's root N, and then there's the same thing with plus. And I get the confidence interval 3.378, 4.462. So that's telling me if I had a bunch of data sets containing 6 data elements from this distribution, from this normal distribution, And if I calculate the confidence intervals for each of these hundreds of thousands of samples I was given, the 95% of those confidence intervals would contain the true population mean. Okay, so virtually identical to what we did when we knew sigma, but now we're using S in place of sigma, and we're using the t distribution in place of N01 to get our quantile. That's the only difference. All right, so let's beef it up a bit with the example we're going to look at. All right, and this one, I'm going to switch it over to R eventually, okay, and show you where I got the red values. But for now, I want you to pause, copy, and play. All right, so now I'm looking for a 99% confidence interval for the mean weight of baby girls born in North Carolina in 2004. Okay, so we've got that 2000 NC Births 2004 data set that contained a random sample of babies born in North Carolina in 2004 and lists their weights amongst other things. So now we're just going to look at the girls in that list. And I'm going to do some of this via R, but let's just talk through it first and then go back to the R and see how I got it. I can calculate the X bar. I can calculate the standard error. I can calculate how many girls there were in that sample data set, and then N-1 would be 520, okay? I'm also going to make sure that the data of these girls is normally distributed or looks normally distributed. But nobody's told me it's normally distributed. Nobody's given me the sigma, the standard deviation of the variance, right? So I don't know any of that. So that's why I calculated S. Now I do want a 99% confidence interval. So my alpha is 0.01, thus alpha over 2 is 0.005. And so I need that t distribution quantile, t distribution having 520 degrees of freedom. So I'll type in QT 0.995, 520 and get 2.585. Now, once I have all these ingredients in red, I can use that formula you copied down from the first panel. X bar minus quantile S square root of n. And then the same thing with plus. And I get a 99% confidence interval between 3343 and 3453 and change grams. Okay. All right, now let's look at the R code that gave me the red values. So this is on your chapter 7 R file, and I've already got it open here. Okay, so I'm on line 58 of the code, and that's where it says example 7.6. Now I just opened R, so I need to make sure I've got my resample clicked, because I am going to be grabbing sample data or data from an actual file here. So there's resample click. Okay, so line 60. I'm going to look at the NC Births file, but I'm going to select only the column weights and the subset gender only that lists female. And I'm going to drop all other values. I'm going to define this new vector to be girls. So this is just going to give me a big old vector of girls' weights. Okay. And then I think I forgot to do this, but I think I want length. Helps to spell it. Girls. I'll save this so you folks don't have to do it. Okay, and there, I get 521 down below as my output. So that's where I got my N value. All right, let's look at this data. Let's do a QQ norm plot to see if it looks normal to us. So that's line 65. Looks pretty normal. I can throw the line in there. And that's a pretty good normal fit. So it sure looks like this girl's birth weight is normally distributed. Calculate the mean. There it is. That's the value I have on the board. Calculate the standard deviation. That's the value I have on the board. Calculate my quantile. That's the value I had on my board. So that's where all these values are coming from. All right. Now, if you happen to be really, really lazy, you could go down to line 74 and you could do the following command. T-test on that vector girls, confidence level 0.99, and just do $conf. And if you look, you get 3343, 3453. So pretty much the exact same thing. Let's see. Just save this. I get rid of the $conf. What happens? I think I get a whole bunch more information. Yeah. I get the confidence interval, I get some extra information with p-values, degrees of freedom, t-values, all kinds of different things, right? Which we don't quite know all the ingredients for that yet. Right, so that's how I can get R to assist me with real data sets. All right, so now last panel in this video, we're going to finish up with this iteration and list some assumptions that we need. Okay, so why don't you pause, copy, and play. So this confidence interval formula we've been using when we know it's normally distributed and we didn't know sigma, it's got some assumptions. We assumed the underlying population was normally distributed, okay? That's why we just checked it on that R code. Now, if it's not, but if the data does look to be symmetric and you've got a pretty large N, then this T-based confidence interval is relatively accurate, okay? If the underlying population's distribution is not symmetric, then we got trouble, all right? However, the larger the N value, the more skewness, the more unsymmetry we can handle using this T confidence interval. And there's whole chapters of study sort of saying, okay, well, how large does N need to be with this skew value and that sort of thing that we're not going to be getting into, right? Now, one thing to note is that sample mean can be sensitive to outliers. So it's oftentimes, if you do see you've got outliers in your data, which QQ norm plot can show you, or just a scatter plot could show you, it's probably best to remove them or do a trimmed mean, and then simply report this with your result. You could say this is a confidence interval using a trimmed mean or tossing out outliers.